And we have 3 exciting future events in the works. The first is going to be an art ceramic webinar. We're also working on a diversity in ceramics webinar. And we're also working on a student focus webinar, and they'll be coming up in the future soon. And just so everyone knows who's helped put all of this stuff together, the NorCal team consists of Adrian Radosa, Andy Nito, Jenny Beach, and Sammy Zhu. And we've been expanding, and we've gotten some additional members to help out with putting together these events. David Ho, Daniel Chafee, and Laura Roberts. And then finally, we have our advisory team, Sylvia Johnson and Jim Shackelford. Okay, so with that, I'd like to shift over to our stars of the show. Our first presenter is Chris, and he's the co-founder and managing director of Tandem PV. So Chris, if you could take the stage and start off with your presentation.
Great, good morning. Scott, if you could unshare, then I'll be able to share my screen.
I can do that.
Perfect. Good morning, good afternoon, good evening, wherever you are. My name is Chris Eberspacher from Tandem PV. We're a small startup here in Northern California developing new technology to convert sunlight directly to electricity using photovoltaics, and in particular to make tandem devices to make high efficiency, capital efficient photovoltaics. Let me start by talking a little bit about photovoltaics itself. You might well have seen photovoltaics on a rooftop in your residential neighborhood, but it's only one of 3 major areas where photovoltaics is now present. Here in the upper left-hand corner is a somewhat out of the ordinary, quite beautiful photovoltaic rooftop that's now being marketed by Tesla. Far more common are individual modules. Individual modules are now mounted in quite large volumes on large commercial industrial buildings. And then a third application, which actually constitutes a significant fraction of the total installations, are large ground-mounted arrays, either fixed arrays or arrays that are on trackers that further amplify how much power comes out. Now, this is all part of a shift to low carbon electrical power, and in particular, the emergence of cheap, reliable renewables, in particular here in the US. If you look at solar photovoltaics in particular, it now constitutes about 20% of the electricity generated in California. A little bit less, maybe around 10% averaged over the full nation. But to give you a sense of it, in the first quarter of this calendar year, 40% of the new electricity adds were in photovoltaics. The considerable advantage that photovoltaics is now delivered on still needs to be further increased in order for photovoltaics to really be a core foundation for a future of clean electric energy. On the top, you get a sense of a local household here with maybe a typical photovoltaic system. This is just a shot we took of somebody's house while we're driving down the street. If those modules are for a system averaging maybe 13%, it quite probably is enough to power that entire house. On the other hand, if you would like to power that house plus all of its other non-electric energy needs, so for example, to convert from natural gas water heating to electric water heating and space heating, then you need to probably double the efficiency, upwards of 25%. And if you'd like to charge electric vehicles for your use as well, then maybe up to 35%. The difficulty is that photovoltaics today is somewhere in between in that 18 to 20% range, and 25% is beyond the reach of current single junction technologies. So you would like to get more efficient in order to be able to put more power on the roof. Now this also drives down the total delivered energy cost. if you look at a module today of maybe 18%, and then ask yourself, well, what could the very same installation with 30% efficient modules, basically, even if the module price doesn't change at all, you generate more power, and that better amortizes all of the non-module cost. And so you're able to decrease the total cost of the system, and because of that, of the delivered power, by upwards of 25, 30% or more. And then lastly, if you look at photovoltaics as one of the contributing technologies to trying to temper global climate change, what you'd like to do is to increase the capacity of photovoltaics manufacturing by at least an order of magnitude. Today, people make and sell about 100 gigawatts per year of photovoltaics, and they've spent roughly $100 billion to install that capacity. And so to go up by orders of magnitude is a very large capital call. So you'd like cheaper capital costs for photovoltaics as well. The traditional technologies for photovoltaics are well known, I'm sure, to everyone on the webinar. The one that dominates is crystalline silicon. Over the course of the last 3 decades, crystalline silicon has increased and pretty much reached its technological limits on efficiency. A technology that can deliver even higher efficiencies are 3,5s, for example, gallium arsenide. You can see that gallium arsenide is considerably more efficient. Unfortunately, gallium arsenide is probably more than a factor of 10 more costly as well, in large part because of the cost of the wafers. Even if you look at crystalline silicon, a big part of the cost of crystalline silicon is the cost of purifying silicon, growing ingots, cutting wafers, making cells, etc. And so for quite some time, people have been interested in thin film materials where you use perhaps 1/100th of the amount of material. And because of that, you can reasonably project lower materials costs. The good news is those also have improved. The bad news is they're reaching their technological limit, and the economies of scale so far have continued to favor crystalline silicon. So the good news is crystalline silicon works well. The bad news is it's near its limits, and we still want to increase by orders of magnitude. A new material that's arrived on the scene in the last 10 years have been a material, perovskites. It's a thin film. It has very high optical absorption, so you can use very thin layers. It's able to be processed with low-cost non-vacuum processing, and so the projected cost of perovskites is quite low. And it also has low defect densities and easy crystallization, and so its efficiencies have rocketed up to be comparable with those of the established technologies. But perovskites also open up a second opportunity, and that is, instead of viewing perovskites as competitor with all the other technologies, you can view perovskites as something that can be done with those technologies by combining perovskites with one or more of the other technologies in so-called tandem devices. And to give you a feel for that, you need to understand how a photovoltaic device is made in the first place. So if you look at 95% of what's made and sold today, it's all based on crystalline silicon. So you take sand, reduce it to metallurgical grade silicon, purify that into ultra pure silicon, grow an ingot, slice that into wafers, losing about half of that high purity silicon just in the slicing operation, and then convert those wafers into cells, and then assemble a set of cells together in an electrical circuit. The good news is the cells work quite well. They can last for a long time. The bad news is they're rather fragile. And so in order to protect them, you can't put this on the roof of your house. Instead, what you do is you put a heavy piece of thermally tempered glass and bond it on top of the cells. And then, so the installation guys don't break the piece of thermally tempered glass. Usually there's a metal frame that goes around to protect the glass. And so what you see on the roof is an integrated panel, which has individual solar cells, but basically has a encapsulation strategy that has glass in the front to protect the cells, and a metal frame typically, and some kind of polymeric backsheet to keep water away from the back of the cells. These devices are quite rugged and durable. A typical warranty for crystalline silicon is maybe a quarter century, and they're likely to last half again or more as long as that. Competition has driven the cost structure down. That's the good news. The bad news is competition's also winnowed out the gross margin possible. And so the photovoltaic industry, 95% silicon, all working with very tight margins. And because of that, hard to scale that extra factor of 10. Along come perovskites. Perovskites are thin film materials. You can deposit the perovskite on the piece of glass that's going to be used as the cover glass to the silicon. And then you have not one, but two different photovoltaic circuits. The perovskite circuit, which is tuned to work with the visible light and be transmitted to the infrared. And the silicon continues to generate power from the infrared light that goes straight through the now perovskite coated cover glass. And when you assemble those two together, put a frame on it, now you have a tandem module, which works at least half again as well as what silicon does. So maybe 18 to 20% silicon today, 25, 30%, maybe up to 35% of maturity tandem modules, simply by adding perovskites to the cover glass. So, and then the second is that the only thing you're doing in the module is putting the perovskites on, so the differential capital cost is quite low, and the amount of power coming out is quite high. So if you look at the cost of an installed system, you get a significant decrease in that capital cost. And because of that, the opportunity for better scaling. Then perovskites. What are perovskites? Well, perovskite actually refers to the crystal structure. So if you look up perovskites on the internet, it's a mineral, calcium titanate. And what people figured out at universities in the last decade is if you took calcium titanate, stripped the oxygens off, put halides in their place, got rid of the calcium and the titanium, and put other cations in their place, in particular, generally a metal in this B location and various organic cations in the A location, but still had that perovskite lattice structure, you're able to make tunable, high quality semiconductors that are very well adapted to photovoltaics. So you can also change the composition. So a base case photovoltaic perovskite is methyl ammonium lead iodide. Since the photovoltaics industry tends to be populated with electrical engineers, mechanical engineers, physicists, and only a few chemists, most of us simplify the writing. So methyl ammonium lead iodide to make what is often referred to as MAPI, methyl ammonium lead iodide. If you then go and start to shift the cations from methyl ammonium to, for example, formidinium, cesium, rubidium, etc., and more importantly, if you start to shift around the halides and blend in particular, bromine, you can start to uniformly adjust the optoelectronic properties of the perovskite from a fairly narrow bandgap material that can make an efficient solar cell all by itself to a fairly wide bandgap perovskite material that is well designed for that upper layer of the tandem device that I showed you on the previous page. To first order, it's pretty simple to make these materials. They can be easily solubilized in polar solvents. So if you want to make something simple like MAPI, you can take methyl ammonium iodide, lead iodide, dissolve it in DMF, then print or spray a thin wet film, dry that thin wet film into a intermediate stage layer, and then bake that layer to crystallize it at relatively low temperatures. And so in a simple laboratory bench scale setup, you can already make reasonably efficient solar cells, 18, 20% or more, using materials that can be easily varied. That's the good news. The good news is it's relatively easy to make. The bad news is as always, there are complications. So true, you can just take simple methylmonium lead iodide, dissolve it in DMF, but they have different solubilities. So while you're drying that layer, you tend to get segregation. And because of that, you get small grains with various compositions. A way to try to mitigate that is with fast drying. So people have done a variety of ways of fast drying, everywhere from forced convection to heat to vacuum to most commonly using so-called anti-solvents to basically rapidly displace the DMF with something that the salts are not soluble in. But these anti-solvents pose their own, if you will, industrial hazards given the nature: chlorobenzene, dichlorobenzene, diethyl ether, etc. Second thing you can do is you can add various additives to try to control the crystallization. A typical additive is one that complexes with one or more of the constituents. Those are now very widely used, as are various faster to volatilize solvents and recrystallization strategies. But all of these strategies get more complicated when you start to use multi-cation compositions in order to get that wide bandgap. So, and then more complex yet when you complete all the rest of the layers in the cells. So to leave you with the final thought, so perovskites, quite promising, in particular as a opportunity to make high efficiency tandem devices. The high efficiency tandem devices open up the opportunity to leverage the existing infrastructure, in particular the infrastructure of crystalline silicon photovoltaics, and then make tandem devices that produce maybe as much as 50% higher efficiencies and perhaps 30 or 40% lower delivered electricity costs. So that gives you a quick overview. What Tandem's doing, as the name suggests, is to develop this so-called mechanically stacked tandem structure. And as a startup, we're in that stage of going from things you hold in your hand to things the size of a dinner plate. And then a typical manufactured module is something about the size of the desk you're sitting at. So that gives you a feel for it. Questions then?
Excellent. That was an awesome presentation. So we'd now like to open the floor to questions. If you have any questions, down in the bottom right corner, there's a Q&A. If you click on that Q&A, you're able to type your questions. We'll receive your questions and then we will ask Chris those said questions. So feel free to start asking away. So we've got our first question, is from Daniel Chafee. It is, how is the collector grid integrated to the tandem layer?
So there's two basic strategies, for example, to make a perovskite silicon tandem. One strategy is to take a silicon solar cell, deposit the perovskite material directly on the solar cell itself so that the tandem structure is monolithic. And so a monolithic cell requires that the grids on top of the crystalline silicon cell probably be replaced with perovskite and then grids on the perovskite. So that has to be integrated together. On the other hand, what we're doing is making the so-called mechanical stack, where you have your silicon cell, and then you have the perovskite that's on the cover glass. And in between the two is a non-conducting encapsulant material, which is always used simply to mechanically buffer between the fragile silicon and the glass. And so there is no electrical contact between the perovskite and the silicon until all of the wiring reaches the junction box, where there are power electronics to mix the two. So the short answer to Sylvia's question is there is no connection to the grid.
Awesome, thank you very much. So next question is, how big is Tandem and what kind of people do you guys employ?
So at the moment, Tandem is 7 people. There's 4 of us here in California and 3 of us seconded at the US National Renewable Energy Laboratory just outside of Denver, Colorado. The people that we have on staff are a trio of chemists, as the ink comments might suggest, a mechanical engineer who got his PhD in material science, a physicist who got his PhD in applied physics, and then a electrical engineer, and then a gentleman out of the paint industry who is very familiar with how to mix and coat solid ink layers. So it's a range of skills.
Nice, you got a lot of variety there. That's awesome. So the next question is, are these tandem panels meant for residential use, industrial use, or kind of everywhere?
So the first answer would be everywhere. On the other hand, as anyone that's developed a small business, in particular a Silicon Valley startup, you have to look for where can you get the most impact early on. In the case of making a very high efficiency module, the real bonus comes from installing it in a system that has high non-module costs. So the more efficient module better amortizes those non-module costs. And so that typically is residential rooftops. And so I think what you'll see is you'll see tandem devices used in residential rooftops, because at least 50% of people who buy photovoltaics today to put on the roof of the house end up telling their installer that had they had roof space, they would have put more power on. So there's a real demand for it there, and the economics are best there.
Okay, another question. Are you developing new perovskite materials, or are you developing new and efficient devices? What range of the spectrum are you guys there?
So our particular area of expertise is in scaling. And so if you look at perovskites today, it's become the hot topic in photovoltaics. And so there are thousands of laboratories around the globe working on it. And people have tried all manner of different compositions, different ink additives, different strategies. What's very clearly lacking is how you go from maybe something which is a square centimeter to something that's measured in square meters. So a typical module is maybe 1 by 2 meters in size in production. And the vast majority of the work being done is being done on things that are the square inch at tops. And so what we do is quite a bit of chemistry, quite a bit of physical science, some crystal work from the ceramics point of view, but it's all targeted towards scaling.
Excellent, so a good mixture. So one last question then. So if I wanted to get a tandem solar panel instead of getting a silicon, one of the older solar panels, how would I go about getting one?
At this point, you would patiently wait for a couple more years. So we now make things about the size of your open hand, roughly 20 centimeters squared. And what we anticipate doing in the next 12 months is scaling that up to that meter size. And it'll be at least another year before a commercial product comes out after that.
Awesome, awesome. Thank you so much, Chris. That was a great presentation. I feel like I know a lot more now about solar cells and that sort of stuff. That's excellent.
Thank you.
Champion. So next up, we have Christine, who's the co-founder and CEO of Imprint Energy. So Christine, if you would like to take the stage and start presenting your stuff, that'd be awesome.
Great. Let me go ahead and share my screen. Oh, and hopefully that's visible to everyone. Thank you so much. I really appreciate this opportunity. I'm actually really excited to share some of my own sort of personal journey in being an academic researcher that started a company and is now leading that company towards, you know, our commercialization goals. So this is meant to be a bit of like a personal retrospective, as well as some information on the company. At any point, you know, feel free to send questions, and happy to answer them at the end of this presentation as well. So my name is Christine Ho. I'm CEO of Imprint Energy, co-founder and also primary inventor of the technology. At Imprint, we essentially are making trusted, safe, high performance batteries that will help electronics blend into everything. And this technology essentially is a printed or flexible battery. And if you Google that, flexible battery or printed battery, you'll probably see Imprint images. For a long time, we have been at the leading edge showing that batteries can be interesting shapes and sizes, and they can live on surfaces that have never had electronics before. The technology comes from a material science innovation. This was actually developed at UC Berkeley during my PhD. Essentially, we have taken a zinc and manganese dioxide battery and developed a solid state electrolyte such that the entire battery can be solid state and printed using screen printing. So every one of these layers can be screen printed. They'll start off as an ink that look like acrylic paint essentially, and can be patterned into interesting shapes and sizes. And by printing one layer on top of the other, we essentially can build up the battery sandwich or battery stack. And over the course of Imprint's life, we've been focused on developing a pretty heavy IP strategy. We have over 17 patents granted at this point and a number pending. But we also have a number of trade secrets and know-how that we keep in-house just to maintain complete security over the IP. And a lot of customers are looking for interesting portfolio of features, including some sort of form factor definition, whether it's thinness or a really unusual shape. It's not unusual to hear customers ask for donut-shaped batteries as an example, which is hard to do with conventional battery manufacturing. This chemistry is rechargeable, very energy and power dense, and the zinc battery is inherently safe and stable. There's no risk of potential catastrophic failures, no risk of fires, no leaking. So really changes the profile in terms of safety and also greenness and disposability for a lot of these applications. One nod to just the performance. When we first started the company, what we noticed was that especially in compact volumes, a lot of the conventional battery chemistries like lithium ion and lithium metal are very sensitive to moisture in the air, and so need a lot of hermetic packaging, essentially metallized bags or metallized cans. And so as you get to more unusual shapes, more compact shapes, you end up giving up a lot of volume to inactive packaging. And so therefore don't have much volume left for active materials. So even from the get-go, we were able to show an energy density advantage just purely because zinc chemistries are much more environmentally stable. They're just not as sensitive to these sort of environmental moisture and gas. And so we could use thinner and less sort of volumetric packaging and just fit a lot more active material in that given volume. And since then, like any battery company, we've continued to push the energy density and power density of the battery, including cathode innovations, electrolyte innovations, and also just architectural changes to really augment the performance. So we've been able to differentiate ourselves from a performance standpoint against a lot of competitors, especially in some of these compact applications that we're focused on today. The design freedom, I think, is a really exciting part of the technology. We essentially can give customers the ability to design the battery rather than having to design around it. This becomes really important. For example, there was a medical customer that we were working with. They were essentially developing a continuous glucose monitor, and that sort of wearable patch is really unique in that there is a needle with a sensor that is in the middle of that patch, and it goes underneath the patient's skin. And so the electronics have to actually sit in the perimeter around that needle. So they literally wanted a donut-shaped battery. And again, that was something that was just not possible with conventional battery shapes and chemistries. So our battery was sort of a natural fit to give them that form factor and maximize the amount of area to provide them the longest runtime for their application. And again, in terms of just safety, you can cut these batteries, nothing will leak out, there's no risk of failure. So especially as more and more electronics are going to be incorporated on our bodies or in our homes, in our environment, that safety profile is really critical, and one that a lot of product designers are very cognizant of, because they don't want to expose their customers to any sort of risk or potential failures. From a market standpoint, we are focused on this big juicy market, this huge wave of IoT products that are coming. They're literally talking about trillions of devices and things that will ultimately have some sort of sensors and communication capability. In the near term, we're really focused on two major areas. One being in the logistics space. There's a lot of wasted energy and money that goes into moving goods all over the world, including pharmaceutical vaccines and drugs like the COVID vaccine that are very temperature sensitive. And there have been lots of losses in the supply chain, nearly 50% and billions of dollars lost to vaccines being exposed to high temperatures and rendering the vaccine not usable, or any sort of damage along the supply chain, or even tampering and counterfeiting. And so these type of battery powered sensors can ultimately give total visibility of that product as it's moving through the supply chain, and guarantee its efficacy once it's actually needed to be used. Similar story for food products as well. Over 50% of food products are wasted in the supply chain as well. And so we can really make these processes more efficient with these battery powered sensors by applying these sensors like labels or into the packaging of these products. On the medical side, we're focused on a lot of on-body patches and wearables, as well as medical labels that might wrap around your asthma inhaler or your insulin pen and detect every time you're actually keeping track of your prescription and staying up with your prescription recommendations. It can also track if the dosages of those devices are accurate, just in case you're not getting the right amount of that drug. So, you know, these type of products will just make it easier to give high quality real-time data so that we can better manage our health, our lives, and better manage the infrastructure around us as well. So I wanted to jump into more of like a personal discussion of, you know, where Imprint started and how we grew to where we are today. A lot of people, when they ask me about Imprint story, they ask a lot about this transition period going from technical research at the university to making that leap and essentially starting the company and growing from there. And so I thought I'd focus there, but really kind of give sort of give a sort of retrospective on our journey from that point. So like maybe many of you on this webinar, I was a material scientist by training, a lab researcher. I love being in the lab, and I love just solving really hard problems, and batteries are very difficult. So the problems were very challenging. So I spent a lot of time at Berkeley through my undergrad all the way to grad school, and just got really lucky. I was able to join a battery research group, and originally was looking at lithium-ion batteries, but then ultimately transitioned to non-lithium zinc chemistries and different manufacturing methods. So when I was wrapping up my PhD and about to graduate, I was able to actually publish my work and you know, talk about that to the outside world. And what I found was that there was actually a lot of industry interest and feedback. And so, you know, because of that, it created some pull. You know, I started thinking, you know, how do we get this technology out into the real world? And so I actually joined a class called Clean Tech to Market, which was offered by the Haas Business School at Berkeley. And they assigned a group of business students, law students, engineers, policy students to my invention, and essentially for a semester developed go-to-market strategies, interviewed potential customers or partners and investors, and really just codified that there was a real interest in this technology and a potential pathway to commercialize that. And I ended up meeting my co-founder through that class over here on the right, that's Brooks Kincaid. And so you know, after that class, it created some emotional pull, you know, in me and my co-founder. We thought that there was really something special here, and we decided to start Imprint. And so Christmas of 2010, we incorporated the company, and we started by applying to business competitions. We needed money to even, you know, do any level of science and technology development. So we entered a local business competition at Berkeley, and we won. And we got a big check, and you know, it was like the first check was actually around $7,500, and we were really excited. We thought we had a lot of money, and we really got things started with that initial business funding. We hired, you know, our first interns. We bought some materials. We paid Berkeley essentially to be able to continue to incubate on campus, but keep our own IP and develop the technology further. And then we really kind of grew momentum from there. We entered more business competitions. The checks got bigger. And so over the course of Imprint's life, we probably raised about $75,000 to about $100,000 worth of business winnings. And that just really kind of got things going. We spent that early money buying our first manufacturing screen printer, and, you know, our first materials, and tried to build an initial team with interns and early employees to make our first demo. And this demo really kind of revved up our momentum. It was really a simple demo, very crude actually. It's just a business card that we hand painted our batteries and hand patterned a circuit, but you can see when you fold the corner of that business card, essentially lit up an LED that dotted the I in Imprint. And we were able to actually put that business card in investors and customers' hands, and it really got them excited because they saw how simple this technology was, how easy it was to deploy, and how different it was from conventional batteries. So that helped us really kind of gain traction with grants and then ultimately customer projects. I like to show this progress report as a way to just showcase, you know, where we were at in those early days. We were just trying to prove that customers wanted what Imprint was making. And so it gave us the ability to actually work with customers and really define, you know, what were they looking for, and essentially created the R&D roadmap for the company. We were small, we were 2 people for a while, and then, you know, kind of grew to about 6 people, incubated on campus, making maybe tens to hundreds of batteries a day or so. And so for me personally, you know, I felt like I became an entrepreneur. I was really leading the technical team and also, you know, involved in growing the company from the ground up. You know, in our next phase from 2014 to 2017, we transitioned to answering, you know, whether or not customers needed an Imprint battery to which customers do we focus on to actually design this battery in. And so at this stage, we actually raised our first institutional funding with venture capitalists. One sort of feedback is that, you know, working with venture capitalists, you're really developing a long-term relationship. It can take a long time for them to ultimately make a decision to invest in the company. And so, you know, it's really important that you cultivate that relationship from the get-go and really grow their confidence in the company. And we were able to move out into our facility. We're still in this home today. We're in Alameda, really close to the Oakland airport. And we were able to build up some of our infrastructure so that we could grow our ability to make hundreds to thousands of batteries a day. And somehow, you know, within that, we were nominated as one of the 50 smartest companies in 2015. We just beat out Uber and right behind Microsoft. And so we were just gaining a lot of traction with the outside world and putting a lot of emphasis in credibly, you know, presenting ourselves to customers and partners, and you know, gaining their trust in terms of our technology and its capabilities. So in that sort of 2014 to 2017 phase, we started to really hone on which customers could actually commercialize this technology quickly and who should we focus on. We were able to raise funding through institutional as well as non-dilutive forms like grants and customer projects. We escalated our manufacturing capability in-house and also built the team up to about 10 people. And in this time, I actually became CEO of the company, and really my job transitioned from being technical lead to really managing the business itself, you know, managing investment, business development, customers. So my job has really changed over the course of that time. And so finally, in the current stage that we're at, we're essentially entering the market, essentially earning first product revenue. It's been really exciting. Here's some examples of some projects that we've been supporting, including asset monitors that might go into airplanes, and our batteries essentially are the key power source that allows those sensors to be deployed on all different sort of components in these planes. Here's a really interesting project we did with Flextronics, essentially integrating our battery into an asthma inhaler label that could detect the dosage level as well as the cartridge amount of drugs, and essentially remind you if you're running low on the drug in the cartridge. And then also wound care patches, body patches that need to be close to the body, need to be inherently safe and also conformal to the body. This is another project that we supported as well. So, in this phase, we've been able to enter the market and acquire our first product revenue, which has been exciting. We've been able to close some additional rounds to grow the company and ramp the manufacturing. We started working with outside print manufacturers who have the ability to produce these batteries in millions to hundreds of millions of volume. So super exciting. And then we've also grown our own team and actual facility to match the team size. And so it's been really exciting to go from the inventor of this technology, literally hand printing or hand painting one battery at a time, to seeing continuous streams of batteries being made, thousands, hundreds of thousands at a time. So that's just been really personally fulfilling to be able to witness that from the get-go. And then, it's really always exciting when we get to unfurl rolls of batteries in front of customers. It's, I don't think customers have ever really seen batteries made and printed almost like stickers rather than, individual widgets. So I think we've really changed the landscape for how batteries are made and the scales that they can be made at cost effectively. And so one other sort of major transition for me in the last couple of years is I became a mom. I have a 2-year-old son, and had to actually I was growing a baby when I was pregnant while also raising a fundraising round, and had to deal with a lot of really interesting transitions in terms of juggling that work focus along with personal balance. But my son has been a really great addition to our team. He's contributed a lot of smiles and happiness to the team as well as myself, and has been one of our biggest supporters and cheerleaders through this. So I hope you enjoyed listening to my own sort of personal journey and rendition in growing Imprint. And I just wanted to wish you all the best of luck as you also potentially make emotional leaps and transitions in your own careers. I just also want to appreciate how wonderful material science and ceramics in particular have contributed to my own career in enabling new opportunities that are both life-changing but also can really change the world as well. So it's an incredible field, and excited for everyone in terms of their own personal journeys. So happy to take any questions, and thank you so much for your attention.
Loved your presentation, that was awesome. So if there's any questions, again, Q&A, start popping them in there and we will start reading them out. Okay, so first question. Can you say more about what material the electrolyte is?
Yeah, so it's published in patents. Essentially, we have a polymer-based electrolyte. We leverage some ionic liquids in particular to which have really unique properties. They essentially, are molten salts at room temperature, and so have really good sort of electrochemical properties. And we were able to prove that with the zinc chemistry, we could move multivalent ions and the relevant sort of ions in that system such that this electrochemical chemistry is made possible. And then we do use some ceramics to help bolster the mechanical stability of that electrolyte as well. And then what's really kind of incredible is that entire electrolyte can be printed using screen printing, but then essentially stabilize as a solid film such that we can actually print on top of it. So we can actually print in sequence. So incredible material. And again, the material science innovation is really kind of the key to enabling this technology in this company.
No, awesome, awesome. Can you confirm using electrolytic manganese dioxide in the cathode?
Yeah, that is a form of manganese oxide that we use in the cathode. We've been exploring some others as well, just to sort of augment maybe some of the potential capacity or even power capability. But EMD is a real typical material, really cost effective. So we found that it's also a good potential cathode for our chemistry.
Is the battery rechargeable?
The battery is rechargeable. And I think that's actually one really interesting element of this chemistry, because we've moved away from a water-based electrolyte to something solid. We find that actually the kinetics are much better at the interface between zinc and the electrolyte. So we've been able to stabilize the chemistry such that it can recharge.
How has the pandemic affected your business, especially production?
Yeah, it's a really good question. I think the honest answer is it's had a major effect. In January, we were participating at the Consumer Electronics Show. We had a number of customers featuring our battery and their products. We were walking investors around, and they were marveling at, how far we've come in terms of designing into products. And then, shelter in place hit, and a lot of these companies got quiet and had to freeze their budgets, and so especially the second quarter was really quiet and kind of eerie for us. And so the answer is today, our customer pipeline is pretty different than it was earlier this year, but we managed to actually find really good customers who are very committed to their commercial products. We feel even more confident in them because they're so active even through the pandemic. And so, we've had to absorb a little bit of delay in terms of our own revenue projections and production projections, but we've been able to weather through that. Production has also been challenging because we use outside manufacturers, and so to not be able to go travel and visit our manufacturing partners has been challenging, but we've had to rely more heavily on better documentation, doing kind of virtual audits, even employing people locally to do sort of boots on the ground audits. So we've had to be creative, and it's possible to move forward, but we've definitely had to change our course a bit in order to adjust for this new normal.
No, that's awesome. That's awesome. So when you started the company, did you ever consider not starting a company, or were you hooked right away?
Yeah, it's a good question. First of all, like when I was researching at Berkeley, I never thought about starting the company. It wasn't really, it hadn't crossed my mind, to be honest. And I think for me, this wasn't something that I personally wanted to do on my own, but it was through working in that class and working ultimately with my co-founder, who really kind of represented that, like the business side of things. It helped illustrate a potential path, and it made it potentially possible, and it kind of built the appetite to start the company. But it wasn't something that I had sort of envisioned from the get-go. Another piece is actually my dad is an entrepreneur. He was a CEO when I was in junior high and high school, and it's funny because like when I talked to him about potentially starting Imprint, he stood still and said, "Christine, I don't think you should do this," because he went through a decade himself of pushing a company forward, and it was really hard. He had problems with his health and just traveling a lot. It put a lot of tax on him, and so it was really interesting. I had a lot of signals in both directions saying to start and to not start. So it was a tough decision, but ultimately I just felt this emotional draw to do it, and still feel really committed to bringing a safe green battery technology to market that can help really change the safety and the performance of a lot of products. So yeah, mixed answer overall.
Excellent. It's awesome. It's awesome. It must have been so scary when it all got started, but it definitely looks like it's been going well. Mm-hmm. So next question, what is the lifetime of the battery when it's in the field, mm-hmm. or an application?
Yeah, it depends on how it's used and how it's loaded, obviously. So we have some Bluetooth applications that maybe do health monitoring, and in that case, they're continuously streaming data. You know, every 100 milliseconds, every second, a piece of data is being sent and then transmitted. So because it's drawing fairly quickly, some of those devices may only last a couple weeks, and that would resonate with, you know, for example, like a patch that you'd wear in the hospital for a couple weeks while being hospitalized. In other cases, we have asset tracking sensors where data really only needs to transmit maybe once every 15 minutes, every hour, or even every day. And so when you draw out the use of the battery, you can extend the life to, you know, months to even years. So that's also possible. So really kind of it becomes a conversation between the customer in terms of their target runtime and ultimately the power draw that they're looking for.
Awesome, awesome, awesome. So we actually have some more questions here, and I also had some questions for you, but I think I'd like to leave those questions to the very end, so okay, we can give Nadia some time to present as well.
Great.
So just so everyone's aware too, once everyone's completed their presentations, we're going to spend like another 15 minutes where we can open up to questions for everyone again. But before then, I would like to introduce our final presenter, Nadia, who's the CEO and Chief Designer of Bagaveyev Corporation.
Hello, everybody.
So I would like to let you take it away.
All right, 1 second. Can you see my screen? Can you see this?
Yes, we can see your screen.
Yeah.
All right.
Yes, we can. Sorry, I was muted.
All right. So my name is Nadir Bagaveyev, and I founded Bagaveyev Corporation in 2013 to kind of domesticate space. Basically, what I'm trying to say is that space is a place to live, to work. It's not just Moon and Mars. We shouldn't be focusing on them digging other planets. But also focusing, I'm myself fascinated about living in space, working in space, doing zero-G science, zero-G manufacturing, and kind of aiming towards stars. So for example, imagine a house, like on the picture, which has 8 units. Each of them is 6-bedroom apartment. Each room is an inflated epoxy or inflated glass bubble, and they're connected together and turn into a space station. Although this is kind of a further goal, to achieve it, we need a rocket. We need a rapidly reusable rocket to drop the price of flight to space from thousands of dollars per kilogram to tens of dollars per kilogram. So currently, flight to space costs maybe $20 million per person, per seat. And we hope to price it down to approximately $50,000 per person, or about $50 to $100 per kilogram. So we started in 2013, and this is a first rocket that we've launched with a 3D printed metal rocket engine, first on the planet. In 2015, and 3D printing is one of those fields that is rapidly expanding, and we want to take it to basically to ultimate levels. So after launching this first small experimental rocket, we are shifting to a big league, so to speak, and we are planning to build basically a holy grail of rockets, which is a single stage reusable rocket. As you may know, rockets are usually done in 2 stages. First stage is the one that is burning up to 60 kilometers and then drops down, and nowadays first stage is becoming reusable, but we want to make the whole rocket reusable. So instead of having 2 stages and making each stage separately reusable, we just combine them into one. The attempts to do this were done in the past by Lockheed Martin and McDonnell Douglas, but I believe technology at that time was not as good as now. So with the advent of 3D printing and generative design, we can really drive down the mass of the rocket really, really low, from 15% of a mass structural ratio to about 5%. So here on the picture, you can see a rocket. It's a hydrogen-oxygen rocket, and it consists of 3 spheres. The top one is the capsule, the middle one is an oxygen tank, and the bottom one is a hydrogen tank. The tanks are spherical, which is kind of an innovation, but spherical tanks can be twice as or half as thick than cylindrical rockets. And it's nearly impossible to build those tanks with anything except 3D printing. So the first thing that we're going to do is to build the largest metal 3D printer in the world, which is going to be a 100 feet tall 3D printer and approximately 50 foot in diameter. So here on the picture, you could see a printer with a little robotic arm with the mechanics of it to be able to print the whole rocket, and here for the scale is the size of a person. Another large innovation of this rocket is the Eberspacher rocket engine. So probably a lot of you are not familiar with rocket engines, but most traditional rocket engines are bell nozzle rocket engines. So they have combustion chamber in the center, and the bell nozzle expands the gases to larger diameter. In Eberspacher engine, it's the opposite. We have the combustion chamber, which is this annular toroidal chamber, and the gases are aiming towards the center. So this way, we can get gases which are perfectly expanded at any time in altitude on the ascent to space. So again, rocket engine like that was attempted by McDonnell Douglas, except it wasn't annular, it wasn't circular, it was linear, Aerospike. And now I think with the new technologies, we can kind of come back and revisit this idea and redo it. So one of the biggest problems is cooling. When you return from space, your whole rocket, well, whatever returns from space is going Mach 25 or 8 kilometers per second, and it impacts the atmosphere. And it needs to not melt or not burn up while it's entering the atmosphere. So you could see here, for example, a small simulation of the rocket, of our rocket returning from space at 5 kilometers per second at altitude of 60 kilometers, which is where it reaches the highest heat loading. And we have a lot of heating on the surface of the tank and on the rocket engine itself. Here I'm returning to this picture to kind of describe the problem. So the diameter of this tank is approximately 10 meters. It's a hydrogen tank, and it will be 3D printed using Inconel on the bottom and aluminum on the top. But the tank and engine and the surfaces need to be cooled down actively while it's returning. While the engine itself is not a big problem because it's already a regeneratively cooled engine, meaning that it has walls that have channels through which the liquid hydrogen passes and cools it down. But we have surfaces like this bottom of the rocket, Aerospike rocket engine, and the surface of the tank that also need to be cooled, or at least not melted. So we have a couple of strategies to achieve that. One of them is to use this high temperature ceramics such as zirconium diboride, or we are also looking into carbon-carbon composites with some ceramic coatings to prevent oxidation. And we're looking for partners in industry, in academia, in government to innovate on this. Maybe there are 3D printable ceramics. Maybe there are flexible ceramics from which we can produce the tank itself. Maybe there's a fabric that we can kind of wrap around the tank. Maybe it's possible to 3D print transpirationally cooled ceramics, meaning that ceramics will have tiny holes, and the same liquid hydrogen will be expanded through these holes and actively cool the surface while we're re-entering. Maybe we'll get away from ceramics altogether and just make the whole thing regeneratively cooled during the re-entry using some excessive hydrogen that we have, well, spare hydrogen that we have in a tank. Well, that's about it. It's a tough problem. First, we will start with a 3D printer, and we hope to expend approximately $10 million to build that, and then we will expend another $25 million to build 5 experimental rockets, and hopefully one of them will reach the space and return back. If the whole mass of the rocket is 200 tons, that's including propellants, while the structure will be no more than 10 tons, and payload is going to be another 10 tons. This payload, 10 tons, could be obviously used to do a structure if we're not very good at it, but of course the expense is the payload itself. We don't want to do that, so we will be fighting for every gram of the structure. If all of these things will not be enough, we are also looking at the magnetic accelerator that will accelerate rocket initially on the ground up to 300 meters per second, so almost the sonic speeds with the electromagnetic accelerators, similar to ones that are placed on aircraft carriers for aircraft acceleration. And with these several innovations, I hope we will achieve this holy grail of single-stage reusable rocket that is capable of reaching space and returning in one piece. And another thing about ceramics is we are trying not to use ablatives because we need to be rapidly reusable, meaning that rocket needs to land, I don't know, maybe pressure washed, refueled, and be launched again within a couple of hours, maybe 5 hours or so. So there should be no necessity for in-depth inspections. So imagine the rocket becoming similar to an airplane. Airplane lands, mechanics do some inspections between flights. Airplane is refueled and launched again. So that's the scope of my presentation. Hopefully we'll find some experts in ceramics industry that can accelerate our research and development in this. And of course, investments. Well, that's about it.
Awesome. Thank you very much. So I'd like to open the floor to questions. If anyone has any questions, go to the Q&A and we can start. So the first question we have is, what kind of alloy are you attempting to use to print the rocket? Or is that a secret?
We hope to use several. The basic one for high temperatures is Inconel, but we also intending to use a lot of copper and a lot of aluminum. So we are intending to build a printer with several heads to be capable of printing multi-material composites if necessary.
Awesome. So next question, what would make these habitats self-sustainable?
Yes, of course, it's another large problem of making recycling your waste. It's a separate program that, although I think a lot about it, we haven't started doing it in practical sense. But yes, turning waste back into food is one of those things that we'll be focusing on a lot. And I have some experiments that I hope to build first on the ground. Not dissimilar to Biosphere 2, but on much smaller scale, to see if we will be able to use just solar power to convert all our waste back into food.
Awesome, 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 awesome. So next question, how is the transition from Inconel to aluminium made?
I believe that we will, well, there are several possibilities, and what I think is a most likely one is to print them in layers. So we print a layer of Inconel, and we'll print a layer of aluminum on top of it, and then the layer is thin enough that even when we print Inconel on top of aluminum, the melting of aluminum will not be such a problem that we can create these transitions.
Nice, nice. So are you designing your own printers, or are you depending on significant technological developments in metals and ceramic 3D printing?
We'll be looking into partnering with Trump. That's a German company, and there's another American company, Beam, I believe, from which we will basically quote if their technology is suitable for us, but we're not necessarily depending on anybody. We hope to do it ourselves, but if we find some usable, good partnerships, of course, we will not hesitate to use existing technologies. Ceramics, I don't know yet. We haven't tried it, and we haven't communicated with anybody. So this is one of those places where we hope to find partners.
Awesome, awesome. Excellent. Thank you very much. That was a great presentation. Very informative.
Thank you.
So I think we'd like to open up back to questions for all the speakers. So for these last 15 minutes of this seminar, feel free to ask any of the speakers any questions. So I'll give you guys a couple of minutes to start posting questions, and then we'll start throwing them out to all of our wonderful speakers today. So first question is, what is the roadmap for Imprint in 5 years while still staying competitive?
Yeah, good question. And we're always trying to stay at the leading edge and offer our customers not just what they want, but what they want in the future as well. One way that we've been able to differentiate ourselves is to offer the highest power density across the competitive space. And so while some of our competitors focus on lower power, short distance wireless communication, we've been focusing on higher power and longer distance wireless communication IoT products. So, rather than just focusing on Bluetooth, we've been focusing on cellular and even satellite applications. So things have come down in power enough where our battery can be utilized, but we could still offer maybe 10x runtime against competitors. So one part of our roadmap is always just staying at the leading edge from a power density standpoint. We also want to, once we build traction in the IoT space, this chemistry could go into many other applications. So a next sort of stepping stone might actually be the consumer electronics space. So in that case, rechargeability is very important, stability over the entire lifetime of the device. And so we're, gearing towards larger scale applications and also longer life applications as well. And, my hope is that this chemistry, even beyond me and Imprint, have decades of, new business opportunities that we can enable.
Awesome. So now more of a panel style question. Do any of you have an explicit goal of selling your company after a set of milestones? Or would you like your company to grow and thrive indefinitely? Or have you guys even thought about that?
I would split my company into a sellable portion, which is 3D printers that I'm open to sell to. For example, somebody wants to print metal skin dirigibles or airplanes like a Gulfstream 650 size or yachts like 100-foot size. I'm open to do that, but the rocket and space part I would keep.
Awesome. And why is that? Just because of the excitement of space, or?
Yes, of course. The space is exciting. 3D printers is, they're printers. Let HP do that.
Awesome.
So I can say for Tandem PV, We're a small company that's doing technological innovation that offers a substantial improvement upon what's there, but builds on the existing infrastructure. And to be economic, you have to be at a large scale. And so the 7 of us, arguably in the next 5 years, need to raise $250 million. The most likely place for that to happen are one or more of the billion-dollar incumbents. And so I think we're likely to be acquired, but our plan and our structure are predicated on organic growth.
Awesome, awesome, awesome.
I guess, yeah, just in the same vein, I think there will always be a R&D center in the company that, you know, could potentially persist independently, but there may be parts of the company that we could spin off, and whether they continue to just grow or ultimately, you know, partner to the point of acquisition. I think we're open to that. I think the way we answer this more so is, how do we quickly reach our commercial goals? And if it makes sense to work with a partner or ultimately become acquired as a way to gain more ubiquity and traction in the market, then that might be the right answer for that specific technology and that specific product. So, you know, I think we take a really sort of eyes wide open approach to answering that question at all times.
Yeah, I imagine everything in startups is very fluid, with a lot of different things happening, a lot of different decisions having to be made constantly.
Yeah, especially during the COVID times, day to day, things can change drastically.
A little bit of extra uncertainty, yeah.
Yep.
So the next panel style question is, are you able to find the right talent in the Bay Area, or do you find that you have to cast your net wider?
I like Los Angeles too. Yes, probably aerospace is more there. So when we move into larger things like this 3D printer, I'm considering Los Angeles area, but talent is focused in very few areas for aerospace.
Certainly in the solar field, the talent that we need is readily available in the Bay Area. Cost is reasonably high, but the value is quite good, I would say. What's a bigger problem for us is that there was a time in Silicon Valley where you could combine your in-house talent with scads of outside shops of one type or another that might deposit this, pattern that, machine something else. And unfortunately, a lot of that infrastructural hardware capability is disappearing in Silicon Valley.
My point of view on this is that it's hard to find really good people, and so we don't try to limit ourselves to the Bay Area. There's a number of people on our team that we've moved from all different places, not just because they have the background and experience and talent, but because they actually meet the cultural values of the company, and they resonate with those core values. And so that fit can be really challenging. And so we try to keep a wide net there. You know, we certainly do have a number of people from the Bay Area on our team, but it also can be challenging in that it is an expensive place to live, you know, so the cost to maintain staff here is expensive. But on top of that, it's also very competitive. There are a lot of battery companies in the Bay Area that, and also, you know, just broadly speaking, technology companies that can offer extremely, you know, lucrative compensation packages that we just can't compete with. But, you know, we're looking for people who really will feel rich from the experience, not just, you know, the pure sort of cash compensation, and want to really contribute, you know, at a visceral level to the company. So, you know, we cast a pretty wide net and have definitely brought in people from all different places.
Awesome, awesome. Another panel style question. During the startup period, what was the biggest challenge and the most scariest part? Or just initiating a materials science-based startup, right? Because I feel like with tech, there's not as much initial infrastructure that people may necessarily need, but in material science, you need something to make something. Right? So I'm just curious, what are the sort of challenges going through that? And also were there periods where things may have been a bit frightening, right? Like I'm a bit curious.
To me, the most difficult would be probably finding people, because if you're a small aerospace startup, you're not getting the first people, you're getting people who are not accepted to larger companies or NASA. And the scariest part is just running and extinguishing your rockets when they fail. That's very scary.
That's scary.
Wow.
A lot of adrenaline going there too, I bet, right?
Yeah.
For Tandem started at Lawrence Berkeley National Labs as part of a technology entrepreneurship program that was hosted there, or is to this day hosted there. And so for us, the trickiest part was to go from a area constrained but tool rich environment to a standalone business that was just the inverse, where we had the talent, we had the desire, we could easily get the space we needed, but we went from having ready access to all manner of multi-million-dollar characterization tools to having next to nothing in that regime, and having to rebuild critical parts of that infrastructure that we could afford and build connective networks to fill in gaps.
Yeah, at Imprint, I agree with Nadir. I think a lot of challenges that you face up front have to do with people and the team, and making sure that the team can work well, because you're under a lot of pressure together to deliver, and there can be challenges there. So I think there's a lot of challenges there. Also, hard thing is gaining your first customer, really gaining that customer that believes in not just you and the company, but the product that you have, and also the promise of what it can be. And so, it ends up becoming a very personal relationship with those early customers, because they ultimately have to take a leap of faith to some degree. So that's always been challenging. And I think for us, scariest moment has been, we've had the unfortunate incidents of, not delivering what we thought we would to a customer once. And that was really, really challenging, when you think you're delivering something and it doesn't act in the way that you think it should, or if it fails sort of in the customer's hands or in the field. That is a really stressful and difficult thing, because that's the last thing you want to do. You don't want to break that trust with the customer. And so, recovering from that and getting stronger from that, and ultimately, making a better product as a result, I think those are the potential positive outcomes, but it can be really scary when you're really troubleshooting through that.
Yeah, I imagine it's terrifying. Terrifying.
Yeah. Yep. Mm-hmm.
Okay, so I have one last question for everyone. So I imagine starting up a company is a very big life decision, right? A very big life choice. So I'm just curious, how do you guys think you guys have personally changed from before you started to now? Like, how do you think you've grown? Because I imagine you've taken on many challenges, which has caused you all to grow so much. So I'm just curious how you perceive yourselves before you started to where you are now.
To me, it's now you understand that there's nobody above you, meaning that nobody commands you, so you have to basically invent the world yourself. And you start understanding people more. When you're an employee, you're in this kind of box. You have personal left, right, up, and down. But when you speak with hundreds of people, you understand how different people are, and you have to find, so to speak, an access to every person. That was the biggest learning experience for me.
So would you say that's exciting or scary, or a bit of both?
Both. It was great in some places. It was upsetting in other places. But in general, I'm thankful that I have expanded my worldview. Thanks for being CEO.
Certainly for me, this is maybe the third time around. So Tandem PV posed a different set of circumstances. The first time I did it, very similar to Nadir, shift from the corporate world into the independent entity world. And the thing that struck me most starkly was something that seemed rather droll, which was, as he said, there's no one else to do anything. And so you're forced to not do 85% of each task, but to be responsible for 100% of everything happening, and picking and choosing which things make that cut and which don't, and which ones can be delayed and which ones cannot. For me, this third time around, it's been interesting because I see my co-founder grappling with all of that. I have the comparative luxury of mostly being a creative and not staying up nights worried about how that last 5% is going to get done. And so it's that's quite a nice ride from that point of view.
So it sounds like you've adapted to that procedure, right? That process.
Creative is fun.
Yeah, and I totally agree with Nadir and Chris. You know, for me, one of the challenges over the course of the last 10 years is just feeling perpetually like I am not prepared or not well equipped to deal with the problem that's on my plate, you know, because every day there's a new problem that I've never encountered before, that I've never experienced before, and never had training before to sort of deal with. And yet that's the thing that I have to grapple with, you know. And so so I think, like Chris, over time I've learned, and it's something that, you know, I learned from my dad, that as bad as it can seem, and as terrible or as hard as this problem is, things will probably be okay. and that has been true almost every time, you know, we've had one of those crises or hard things land on our plate. So I think nowadays I definitely I go into things with a little bit more calmness, and you know, even in those hard times, you know, just not let myself feel like things are completely devastated and sort of ruined. So I think that kind of personal coping mechanism has been something that I've been able to build over time. But it can be challenging when you don't feel like you're confident enough, you know, to bat. So yeah, I totally agree with Nadir and Chris that's been probably one of the biggest growth areas for me.
Family and friends are a great support, so don't sacrifice one for business. That's a big one.
Yeah, it sounds like very good advice. No, it sounds like it must be very empowering when you're up against an impossible challenge, yet at the end of the day, it works out.
We'll see.
Yeah. 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 But yeah, I mean, even at Imprint, I've seen some technical miracles and business miracles that you just don't even realize could even happen when really good people and smart people come together. Amazing stuff can happen that you just can't even fathom. And same on the business side, you can feel like, you know, you're not getting the traction that you're supposed to get with customers, and then, you know, suddenly there's a customer that is, you know, completely convinced and they're all in and they want to invest alongside you. So so, you know, you can turn from a bad day to a really good day very quickly.
Yeah, I imagine. Well, I'd like to thank you all for participating. I'd like to thank you all on behalf of the Northern California section, as well as ACerS.
Thank you, sir.
I'm so happy that you guys are all able to take some time out of your busy days and come let us all know about your wonderful startups, and also give us some insight into what it's like to being, you know, leaders of these, you know, new organizations that are just going along in the Bay Area. I think it's been awesome. So thank you all so much.
Thank you again.
Great, thank you.
Thanks for the opportunity. Bye.
Thank you. Thank you very much
Thank
for
you,
all of
Karen.
your, yes, oh, you're welcome. Thank you. Thank you, Scott.
All champions.
Okay, I'm going to go ahead and end the webinar now. Thank you again, everyone.
Bye.
Bye-bye.